Now we will be discussing about quantum numbers. Quantum numbers describe the identity of electron. So say we have carbon atom with 6 electrons. Each of the electron has their own set of quantum numbers. There are 4 types of quantum numbers. The first one we call the principal quantum number. The second one is the azimuthal quantum number, or we can also call this the angular quantum number. The third one is the magnetic quantum number, and the fourth one is the spin quantum number. Here is the symbol for each of the quantum numbers. The principal is N, the azimuthal is L, the magnetic is M, L, and the spin is MS. Okay? Now let's talk about what each of these quantum numbers mean. So first, the principal quantum number. This tells you about the shell where the electrons are present in the atom. So let's go back to the Bohr's model of atom. So we have a core that is made up by protons and neutrons. And then we have the shell. The first shell is the one that is closest to the core. Then we have the second shell that is the second closest to the core. And this shell, we can go from N1, 2, 3, and so on. Now we have also discussed about the limitation of this theory. Now, due to the introduction of quantum mechanics, it is realized that the electron itself is also, just like light, both wave and also particle, or what we know as the wave-particle duality. Due to this, it is not possible for us to determine or pinpoint the exact location of the electron as well as its momentum. And this is what we call the Heisenberg's principle of uncertainty. Yeah, so we cannot determine for sure, we cannot pinpoint exactly both the position and the momentum of an electron in the orbits. Therefore, actually, it is realized that instead of looking like two-dimensional circle like this, the place where it is of high possibility for us to find electron is actually a three-dimensional space that resembles something like a cloud like this. So within this cloud, we can find an electron. We cannot for sure determine whether the electron is here, or there, but for sure, within this colored area, there is a very high probability of finding an electron. So the electrons, they're somewhere here, it's just we cannot pinpoint exactly where it is. And this place where we have high probability of finding electron in, we call them the orbital. Yeah. Now the shape of the orbital is actually derived from the wave function square that we discussed in the previous segment, and the derivation of such wave functions result in different shapes of orbital that is actually hinted in the L number. Now let's talk about L. So L tells you about the subshell, and also the L tells you the shape of an orbital that we will get to talk about a bit later. The subshell goes from 0 to blah 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 to n minus 1. Okay? Now, Moving on to the third quantum number, which is the magnetic quantum number. The magnetic quantum number tells you about which orbital. So among a value of L, we will have, in some cases, several orbitals. And the M goes from minus L to plus L. Okay? And lastly, the spin quantum number. This tells you about the spin of the electron, and normally we draw the electron as half arrow like this, whether it's spin up or it's spin down like this. Each of the orbital, it can contain up to or maximum 2 electrons. So one will be spin up and the other one will be in spin down condition. So we've known so far that if we have, say, n equals to 1, we have the L equal to 0. And in this case, when the L equal to 0, this correlates to an orbital that is called an s orbital. And it looks like a ball. So this is the shape of the s orbital. When L is equal to 0, the M is also equal to 0. Don't forget, the M goes from minus L to plus L. If we have N equals to 2, now we have two different L. We can have L equal to 0 and L equal to 1. When the L equal to 1, we have a p orbital. And in this case, we have 3m. We have minus 1, we have 0, and we have plus 1. And each of these represent a single orbital. The p orbital looks something like this, in which the electron can be found within this area. So it looks something like a balloon like this. And of course, because we recognize 3 different axes, we can call this px, for instance. We can also have py, and we can also have, of course, pz. We can have 3 different orbitals, and each of this orbital is represented by this number. So we have 3 different magnetic quantum number, and each of this quantum number represents one of these 3 orbitals. On the other hand, if we have n equals to 3, then we can have L from 0, 1, and 2. For L0, we can again have M0. For L equals to 1, we can have M minus 1, M0, and M plus 1. While for L equal to 2, of course, then we can have 5 variation. We can have M equals to minus 2, M equals to minus 1, M equals to 0, M equals to plus 1, and M equals to plus 2. Now, of course, we will have 5 different orbitals. For L equal to 2, we call this a d orbital. And we can have 5 different d orbitals. So for the d orbitals, we have 5 different magnetic quantum numbers, meaning that we have 5 different orbitals. We can have the one that is in between the axes, in this case, and of course we can also have this for other axes. So here we have dxy, we can also have dyz and dxz. We can also have the one that is on the axis itself, and this one that we call the dx squared y squared. And lastly, we also have the one that is on the z-axis like this, that we call the dz squared. So there we go. We have all 5 the orbitals, each in between the axis, and other 2 on the axis. Now, normally we don't really draw the orbital quite often, so instead, these 5 quantum numbers, we will represent them in 5 squares like this, where each one of them is -2, -1, 0, +1, and +2. And each of this square represents each of these d orbitals. And later on, we will try to fill the space with the electron like this. Okay, so now we have one square represents the s orbital. We have 3 different squares that represent the p orbitals. It could be px, py, pz, it doesn't matter, because all of the orbital, they have same energy. Px, py, pz, they all have the same energy level. Okay, and then we also have 5 d orbitals. The d orbitals, as we discussed, we have dxy, dxz, dyz, dx squared, y squared, and dz squared. And also the 5 orbitals, they also have the same energy level, just like the p orbitals. Now, within each orbital, we can only fit 2 electrons. So maximum for each orbital, we fit 2 electrons. And Hund's rule, so a scientist, I think he's German, German scientist named Friedrich Hund. So according to his experiments, it is found that the electron will first fill the empty orbitals instead of pairing up. Okay? So if we have, say, P5, this represents 5 electrons in p orbitals. So how do we fill in the p orbitals using these 5 electrons? First, we fill them up. We fill all the empty orbitals first. And then, if there is no more empty orbitals, then after that, we will pair them up like that. So P5 will look like this. The s orbital can fit up to 2 electrons. The p orbital can fit up to 6 electrons, and the d orbitals can fit up to 10 electrons. Now, there is a configuration of electrons, meaning how we fill up the orbitals with the electrons. There is a configuration that we call the half-filled or filled or fully filled. Now, half-filled is like this. If it's D5, or if it's, in the case of P, if it's P3. This and this is half-filled, and filled is when it's full of electrons, which is S2, P6, and D10. What is important to remember is that when the electrons are in half-filled configurations inside the orbitals, this causes an increase of stability.